on demand, as well as our energy savings. So we do the KWH and the KW.
Does that mean in the States they're actually advanced enough to actually pay you money for?
Yes, we like to get paid for the money, yes. Yes, we get paid based on, depending on what the contract is, but it's on the volume.
The price here can go to $10,000 a megawatt hour. At peak demand.
So our relationship is directly with the utility. So they obviously don't want to bring on the additional capacity. So they use services like ours, and they have other initiatives for dropping demand to shed load across their network, right? Because they know tomorrow's going to be 110 degrees in Vegas, and they're going to struggle to generate. So let's see if we can drop some of the load out there. And they call on stuff like us. There's others out there. I'm not familiar with all of them, but we're one of their players in multiple programs they've got for demand management.
And that doesn't happen in Australia?
We've had some talks, but not as much.
There was a company that tried to do demand management, that type of demand management.
Yeah, we are currently in talks with especially up in Queensland, there's demand issues. Not so much New South Wales, South Australia. There's problems there. But not so much Victoria.
We've got a little bit of it here. UTS itself gets phone calls about demand management to manage their central energy facilities.
Okay. Yeah, we're talking to them about
But it's not a weather-based.
Yeah.
Hasn't Tasmania been shedding power and
Yeah.
They just threw it from Benson.
Yeah. Okay, so here's just an example. Hopefully this illustrates a little more simply how it works. But essentially, you have the different tariff rates. You're getting cooling injected into the building at the cheaper rates. It drifts during the more expensive rate, recools again, and then drifts the rest of the afternoon. Right? So if we know that price of energy, and if solar just happens to be a cheaper form of energy, well, that just makes it, I'll talk a little bit about that, but you can see where you can go with solar. If you know the price, we can be a little bit more smarter when we charge and just charge a space. And we did some simulations with that. So just to recap, recipe for optimization, thermal model of the building, utility tariffs, obviously the costs, the weather forecasts, the zone temperatures for comfort, you get your target temperature, and our platform, what we spend a lot of the time around, is getting those zone targets from the cloud down to the building, across all sorts of buildings and topologies and networks and security protocols. Obviously it needs to be reliable, and so forth. All right, so 2 more services. So it's great we've got this algorithm, it's great we can save energy, it's great we can calculate this thermal model, but how do we know we're saving? Well, we need a baseline. So we created another sort of regression model that actually calculates the baseline of a building, energy to outside air temperature. We use that, that's been approved by the OEH actually for doing M&D calculations in buildings and other initiatives, ECM initiatives. Works along the same principles of the optimizer. We collected data, we build the model. That model then runs a second model which does the predictions based on the outside air temperature. And we can predict tomorrow's forecasted weather for a building. We have a service around what we call Predictive Energy Advisor that actually sends to a building operator your forecast for tomorrow, your power consumption will be. I suggest you go and do something different, or we can obviously try to do it automatically with PO. But we have our own sort of energy efficiency product, service, some maths, some algorithm stuff around how we do that. It's an LSR algorithm. We've got a few different algorithms we've been using. And then one of the key things is we do use a lot of good statistical validation to make sure that the model is accurate. And we spend a lot of time making sure that we're comfortable with the validity of the algorithm as well as the customer. Having all these algorithms though is good, but what we found is that we also needed to provide a human element. We needed to kind of hold the customer, the clients through all this information, all this data that they get. We found that operators are either too busy, they've got too much going on, the boss told them they need to cut energy. Oh great, what is this platform? Thanks very much, who are you guys? So part of the package is what we call managed services, which is sort of categorized into these 4 areas, which is really about making sure that the facilities guys, the BMS guys, the operators in the building have a very useful or reliable sort of source, be the eyes and ears for them in their building. We've created a whole bunch of tools that allow them to analyze, as well as ourselves, different trends going on in a building. So we can, one of our tools allows us to take all the different data sets of different data types and different data units, lay them all together, looking for patterns, looking for anomalies. Very powerful, very useful. I think that's it. So okay, so last sort of 12 months, 18 months, we've been working with energy in the States on solar and BuildingIQ. So these are just, what I'm going to just talk about here, some of the results of the simulations and tests we've done with them, and how we've incorporated solar forecasts into the modeling to optimize the space and save further energy than what you would with just a native solar feed into a building. So solar standalone, so these charts are a little bit more academic. So this is just a zone profile of a series of target temperatures that a BMS would send for multiple zones. And you can see it's quite static. There are different levels, different zones have different static values, but that's, 20-odd zones with their various static set points. And of course, if you have a solar building on there, you would drop load. So just explain this graph here. This is the total power. This total power is made up, has been disaggregated into a base load, which is your plug load, your standard load, plus your heating and cooling load, which is the blue load. And then this is your solar profile that's come across. And you can see, obviously, the solar profile, the dotted line is a result of this subtracted from that, which is what we say. All right. So that's just the normal standalone solar. Everything's great. So what happens if you put in this smart optimization, this smart intelligent control? Well, obviously there's the gap. Well, your zone profile looks a little bit different because you're charging the building in the morning, and you let it drift in the afternoon. And then what happens to your actual power consumptions? It does change a little bit as well. There's a much larger dip during the day, and you can see here the optimizer capitalized on all the sort of free cooling it gets during the peak of the sun days and optimize even further. So it used that free energy to cool and offset even harder in that building. So that's great, we save more, we can all do well. But what happens is that, notice that it starts drifting in the late afternoon, and then, I might hit a peak demand charge. What's going to happen there? I need to be careful about that. So what we did on the next simulation, we did quite a few simulations, so I'm just going to talk about these 3, is that this is sort of the worst case scenario. Well, it's going to be a cloudy day, so I'm not going to have all my solar. And number 2, I'm going to change my peak demand to be 150 instead of the 250 that it was. So what sort of profile am I going to get then? So again, you get a much harder, sharper cool in the morning for energy. It's a bit longer, and then you get a second charge in the afternoon where you need an extra bit of cooling. So I've got a cloudy day, I've got a really strict tariff demand. What does my power profile look like? So it looks pretty good. So I've kept, you can see there's a lot of bursts in energy, but we've kept it under 150. We've cooled a lot longer in the morning, and then when the sun came back up after the cloudy period disappeared, we charged again, and we stayed under that. So these are simulations that we've done, and this is sort of intelligently controlling the building. So solar and PO minimizes your total building energy. So instead of storing this excess solar as an actual battery, you can actually use the building, its thermal capacity to store that. You're only limited by the comfort bounds that you set in each of those zones. Right? So you're only limited. So if someone puts a 1 degree, 2 degree, you're limited. But if you get to widen some of that, you can store a lot more heat and cooling in those areas. We're really keen to pursue this further.
Sorry, can I just ask, how do you do that? I mean, if you've got people using a building, and you're using the thermal mass of the building to try to retain that.
So one of the key things, one of the key principles of the algorithm is comfort as well, right? So we need to set comfort limits on the algorithm. The algorithm gets set certain bounds. So it can't go past whatever you and the client agree. So it could be 22 degrees, 24 degrees, and 21. And the optimise will run a bunch of simulations over the comfort range and maintain that. So it gets bounded by those limits. So the tighter those limits, the less movement it has, and it just may just keep it flat like a normal building. So the natural space in most buildings in all these areas is there's a high and low, right? As we've all come in here, this place is warmed up, right? And the algorithm will learn those patterns, right? Especially in buildings, right? They know that it's pretty cold at 6 a.m., but come 10 a.m. and everyone's inside their office, you can measure that temperature rise.
Yeah, I had exactly the same question.
So, BuildingIQ, we're an energy-based service. We use a lot of data-driven modeling techniques, a bunch of services we offer. I won't go into that in any more detail. Yeah, hopefully not too sales pitchy. But there's a lot going on here, and there's a lot we're doing in the space. Yeah, happy to talk to anyone about this.
What's the smallest size building that you think that, I mean, this is obviously for campuses, universities, hospitals, but are you doing?
So the smallest building we do is, Cashier is my colleague.
Is that 10,000 square meter?
10,000. Yeah. We do some stores around the 8, but it then becomes more of a volume play. It depends on your actual equipment. Things like that. And then it depends if people are after demand management or energy management. What's your pain point?
Yeah, so that was the question I was going to ask. Like, with all these variables being put
They're
into-
competing.
Yeah. How do you decide which one to prioritize? Is it usually comfort or cost?
So comfort. So we have a couple checks and balances. So the model will bound itself by the comfort bounds when it's doing its predictions. But we also, when we're delivering it down to the actual building, we have another set of comfort parameters that actually lock it in, and it can't go outside any of those. And then it really depends on the customer, right? If they need to know if they sort of lower the peak demand, they're going to have to spread it out, and it could be more consumption in the morning.